Hello students, welcome to Sri Jayendra's Ring Zone classes. I'm your friend and mentor for coming classes with respect to physics. This is lecture number 2 of our unit Thermodynamics. So let's begin with today's class. In today's class, we are going to discuss the first law of thermodynamics. We have already seen the zeroth law of thermodynamics, and that zeroth law of thermodynamics gives me the detail about the thermal equilibrium, that if two systems, it was the zeroth, if we revise it, it's a zeroth law of thermodynamics, that if two systems are in thermal equilibrium with third system individually, then this two systems this two systems must be in thermal equilibrium with each other. This was the zeroth law of thermodynamics, that if two systems are in thermal equilibrium with third system individually, then these two systems must be in thermal equilibrium with each other. So this was the zeroth law. Now let's begin with the first law of thermodynamics. It states that the amount of heat supplied to a system is equal to the algebraic sum of increase in the internal energy and external work done by the system. So what we can see is it's a delta Q that should be is equal. So that is going to be divided into two tasks. It's one is the delta U and another is the delta W. This dq is equals to du plus delta W, or I should say between any two equilibrium state, the change in internal energy is equal to the difference of heat transfer into the system and work done by the system. So from this it's a du which is equals to dq minus of dw. I hope this is clear. Is it clear? Great. So in this situation, according to this is even said as the law of conservation of energy, that whatever total amount of energy you are going to receive is delta q, that is going to be divided either in this or in this. That let's suppose if a certain segment has been passed through the du, then the another segment would be the dw. So this is the mathematical form. This is the mathematical form of the thermodynamics. While I say that du, which is equals to final energy minus initial energy, and this du should be equals to dq minus dw. I hope this is clear. Is it clear? Now let's look at the sign conventions of the system. That if we say that if the heat energy delta q is added to the system, it is taken as a positive. That means dq is a positive. And if heat is released by the system, then it is taken as a negative. That means it should be considered as a minus of dq. Next, if the work is done by the system or gas expands, the work done is taken as a positive. It's a dw. And if the work is done on the system, or what we can say it's a gas is compressed, the work done is taken as a negative. We are going to discuss about this terminologies delta q, delta u and delta w in more detail, but before we discuss that, let's discuss certain limitations of this law. That this law does not explain about the direction of the heat flow, and this does not explain about the efficiency with which heat can be converted into work. This is the limitation of the thermodynamics. So let's understand what is law and how we can use it. It's a delta Q is equals to delta U plus delta W. So when I say delta Q, it's an heat energy. This is the heat energy. When I say delta U, it's an internal energy of the system. This is internal energy. And when I say delta W, it's a work done. I hope this is clear. So when I say delta Q, I say it's a, if delta Q is positive, that means heat is added, or we should say absorbed by the system. It's a heat is added or absorbed by the system. Delta Q is negative when heat is removed or rejected by the system. Does it clear? Does it? This is delta Q. So that if heat is being added to the system, I should take it as a positive. If heat is taken as a, if heat is removed from the system, then this delta Q should be considered as a negative. Now, next is the delta U, that is what we call as the internal energy. That if temperature of the system, if temperature of the system increases, then delta U is positive. Now the question is why it is something like this, that why internal energy increases if temperature increases. What is the relation with this? So what I can say is that's an internal energy is combination of potential energy and kinetic energy of gas molecules, but majority of part of an energy, majority of part of an energy is kinetic energy. So kinetic energy depends on the temperature. Internal energy also depends on the temperature. Please keep this in mind, that because internal energy, what it is basically the potential energy and kinetic energy. It's an addition of that. But if I look at this very practical way, that it is only be dependent on the kinetic energy only, because potential energy would be a very less, and that very less amount of potential energy can be ignored if I calculate the internal energy of the system. So this kinetic energy depends on the temperature. That's why even the delta U, it's in temperature, it is having a dependence on the delta, on the temperature. I hope this is clear. So if temperature of the system increases, then delta U is positive, and if temperature of the system decreases, if temperature of the system decreases, then internal energy decreases. Have you got this? Have you? Are you sure? Great. One more thing is that delta U is state variables. That means it depends on initial position and final position only. Yes, it depends on the initial position and final position only, and does not depend on the path that we understand. So from this we can say that in the case of cyclic process where initial energy or where initial state and final state is equal, so that means delta U is 0 because change is 0 because nothing has been changed and internal energy remains the same. This is the situation. I hope this is clear. Is it clear? Is it? So this is the case. This is the case of the cyclic process. I hope this is clear. Now one more thing that when I say the when I'm talking about the internal energy of the system, then I must understand that internal energy of the system depends on the temperature as well. Yes, and if it is dependent on the temperature, what would be the value of delta U if I use to have isothermal process? Think over it and let me know. So in the case of an isothermal process, change in temperature is 0. If temperature is not going to change, then delta U would be 0. I hope this is clear because internal energy depends only on the temperature, and that's why delta U is equals to 0. I hope this is clear. Is it? Great. So do you understand what delta U is? Now let's discuss about the work done, that how the work done can be calculated and when work done would be positive and when work done would be a negative. Let's have a look. It's an work done. Generally we denote it by delta W. So what we understood is that delta W is equals to P into delta V. Yes, it's a pressure multiplied by change in volume, and that could be pressure into bracket Vf minus Vi. So if the case is that final volume is greater than initial volume, and this process is what we call as an expansion process, then delta W is positive because Vf minus Vi is greater than 0. But if reverse is the situation, if Vf is less than Vi, that means final state is having lesser volume as compared to the initial state, then it is the compression process, and in this situation delta W is negative. So always keep this in mind that if it is the case of the expansion process, then this delta W, or I should say work done, is a positive, and if a final volume is less than initial volume, or I should say if it is the case of the compression process, then delta W is negative. I hope this is clear. Is it? Great. Now let's look at the next thing about the work done is how to calculate, how to calculate work done. We have a different approaches to calculate the work done. Let's see this. First, it's a delta W is equals to P into delta V. And from this, it's a final volume minus initial volume multiplied by pressure. That is how we can evaluate the delta W. A next approach is that let's suppose we have this graph. It's a P versus V graph. Let's say suppose this graph is given something like this. Yes, it's a expansion process. So for this P versus V graph, it's a P versus V graph is being said. P versus V graph, it's a graph for the P versus V, and what I need to find out, I need to find out the work done. So it's a delta W which is equals to P into delta V. And when I say it's a P into delta V, that means it's an area of P versus V graph on volume axis. Please keep this in mind that this is the area of the PV graph. That is absolutely correct. Even that is understood by you as well, that it's an area of the P versus V graph, but that is to be taken on the volume axis. So when and when you attempt the questions of the thermodynamics, then always look on the that which quantity or what quantity has been given on the y-axis and which quantity has been given on the x-axis. So please always keep this in mind. Always have a look that which quantities have been given. So this is delta W which is equals to P delta V, and this is the area of PV graph on the volume axis. This is the one situation. Next, third, that could be considered as delta W is equals to integration of P dV starting from initial volume to final volume. This is delta W. This is equals to integration of P dV from Vi to Vf. So these are the approaches. These are the approaches that is generally used to find out the work done of a process. I hope this is clear. Do you have any doubts? Do you have any doubts up till now? Is there anything? Is there? Are you sure? Great. So now let's begin for the numerical. Let's suppose the situation is find out work done of gas when relation of P is equals to A into V plus V square, where A is constant from V initial equals to V to V final is equals to 3V. This is what I want. How will I do this? So what I understand is that this is work done which is equals to integration of P dV, and this P could be said it's an A into V plus V square dV. So from this, this is equals to integration of AV dV plus integration of V square dV. So this is equals to A into V square by 2 plus V cube by 3. And what I need to do, I need to put up the value. It's a V to the 3V. So just put up the value and get the answer in certain joules. I hope this is clear. So this can be done easily. Is it? Is it? Great. Let's work for the next approach. That let's suppose this is the graph for the P versus V, and this process is something like this. I need to find out the work done. So the question is find work done on, or find work done of the given graphs. So as you can see this, that this is P versus V graph, and this is V initial, this is V final. So this is V initial, this is V final, and this is a graph of P versus V. So what I need to do is I need to just calculate an area of this. To calculate an area of this, you need to take an area of this. This is the area of this triangle. So it's an area will give me this work done will be in certain joule. It's area on volume axis. Please keep this in mind. I hope this is clear. Great. Let's look at the second graph. That this is volume, this is pressure, and graph is something like this. So now what I need to do is I need to just take this area. Hope this is clear. So this work done, it's an area on volume axis. I hope this is clear. It is that area, that is what we need to consider to find out the work done in this system. I hope this is clear. Has it? Great. So shall we move to the next question? Shall we? Great. Now let's suppose it is the case of the cyclic process, as I know that you know a little about the cyclic process. So what happens in cyclic process? Basically I want to focus on the work done of the cyclic process. We will learn it in detail in lecture number 4, that what cyclic process is and how it behaves. But here I am interested in the to find out the work done of cyclic process. So what we understand is, so first let's understand what cyclic process is, what it is. We can say that if initial and final state variables are same, then system may be in cyclic process. As well as let's call this as a graph, that this is P, this is V, and let's say this is the situation. I hope this is clear. So as you can see that, let's call them a name. It's an A, B, C, D. So work done in AB, it would be 0. Why? Because work done is equals to P into delta V, and location A and location B both are on the same volume. Yes. So work done equals to 0 because delta V, change in volume, equals to 0. Same is the case with the work done in the CD. It would be a 0. Why? Because it's a P into delta V, and delta V equals to 0 in this case. Now I need to find out the work done due to B to C. Let me redraw. This was the situation. Yes. A, B, C and D. So it's a work done due to AB is equals to work done due to CD, that is equals to 0. Now I need to find out the work done due to BC. How will I do this? So to find out the work done due to BC, this is P, this is V. You need to find out the area on the PV graph on the volume axis. So work done due to BC, basically it is something like this. You need to calculate the area of this complete. You need to find out this area. I hope this is clear. It is, let's call this as an area 1. Now, and this work done, it's a work done due to process BC, is positive or negative? Yes, it is positive. How could I come to know? Because it is the expansion process, as we have learned before 2 to 3 slides, that during the expansion process work done would be the positive. Now it's a work done due to D2A. So if it is a work done due to D2A, you need to calculate a second area which we call as an A2, something like this, and this is negative. Why? Because this is the compression process. This is the compression process. So if it is in the compression process, net work done, it's an area 1 minus area 2. So if you look at this area 1 minus area 2 very carefully, you might get it that it is the area of cycle. Yes, you need to find out the area of the cycle only when this processes are the when this processes are just the cyclic processes. I hope this is clear. One more thing, that if cycle is rotating in clockwise, then work done is positive. So if cycle is rotating in clockwise, then work done is positive, and if cycle is rotating in anti-clockwise, then work done is negative. So if cycle is rotating in clockwise direction, it is just the positive work done. If cycle is rotating in the anti-clockwise direction, then the work done is negative. I hope this is clear. Is it? Are you sure? Great. So let's have one of the question based on this concept. Let's say this is P, this is V, and this is the process. It let's A, B, C, D, A to B, B to C, C to A, and again D to A. That means from A, this is going to be repeated, and this is known as the cyclic process. So if I want to find out the work done of this, the question is find out work done of given process. So it's in work done due to AB, which is equals to positive. It's a work done due to CD, it's a negative for sure. Yes, because AB, it's an expansion process, CD, it's an compression process. I hope this is clear. To find out the work done, let's call this as a 2V naught. This is 4V naught. This is P naught. This is 2 P naught. So work done could be written as, this is basically a rectangle, and rectangle, to find out the area of that rectangle, it is the multiplication of just two slides. So it's a 2p naught minus p naught, that is equals to p naught multiplied by, this is 4v naught multiplied by 2v naught, it's a 2v naught. So this is equals to 2 into p naught into v naught. This is the work done in the cyclic process. Have you got this? Have you? Do you understand this completely? Do you? Great. Ready for next question? Let's suppose they said that if 100 joule of energy is given to the system, and from this 100 joule, 30 joule is being used, 30 joule is being used to increase the temperature of system. Find work done. You need to find out the work done. How will I do this? So what they have given is that they are having the 100 joule of energy is given to the system, and when they said that this is the amount of energy they had that has been given to the system, that means this delta Q, which is equals to plus 100 joule. I hope this is clear. And from this 100 joule, 30 joule 30 is being used to increase the temperature. As temperature increases, delta U should be a positive, so this is plus 30 joule. What I need to find out? I need to find out the work done. So delta W, or work done, is required. So basically this is delta Q is equals to delta U plus delta W. This is 100, this is 30, so this is remaining, and that remaining would be, in this case it's a 70 joule. Even this is positive, so from this we can see that from this gas is going to expand, because delta W, it's a plus 30 joule and this is the positive. I hope this is clear. Is it clear? Are you sure? Great. Now let's look at the very important question, that if total energy given to the system, is delta Q, within which delta U has been, within which delta let me rewrite this. So find out fraction of this total energy used in, find out fraction of this total energy used in, or used to, increase internal energy. How will we do this? Let's assume that gamma is Cp is to Cv. So we have been given the total energy, and that total energy would be the delta Q. I need to find out the fraction of this total energy used to increase internal energy. So let's suppose understand that initially that is the delta Q is given, and let's suppose this delta Q is done at constant pressure. So it is NCP delta T, and delta U, it's an NCV delta T. You want to find out the fraction, it's a delta U divided by delta Q, because total amount of energy is U, and within which delta U has been used. So this is equals to NCV delta T divided by NCP delta T. This has gone, and this is equals to 1 by gamma. This is what we call as a delta U by delta Q. And if I want delta W by delta Q is being asked, then what I can do is, it's a delta W by delta Q is equals to 1 minus it's a delta U by delta Q. So this could be 1 minus 1 by gamma, which is equals to work done, or I should say change in work done divided by change in energy. It's a delta W by delta Q, 1 minus 1 by gamma. Please do remember this. This is having a very good applications based on this questions. Yes, would you like to have one of the question based on this? Let's say that if total energy added to the gas system, if total energy of, let's suppose, 100 joule is added to the gas system, within this how much energy is being used, then within this how much energy is being used to increase temperature, and let's assume gas is diatomic. So they said that total energy of 100 joule is added to the gas system, and within this how much energy is being used to increase the temperature. So increase the temperature, that means I need a delta U by delta Q, and that is equals to 1 by gamma. I hope this is clear. So from this, it is the delta U is equals to gamma times of delta Q. It's in gamma. Now the gas is diatomic, yes. So this is 7 by 5 multiplied by delta Q, it's 100. So this is equals to 27, it's a 140 joule would be the internal energy. I hope this is clear. Is it clear? Do you have any doubts? Do you? No? Great. Now let's look at certain quick questions. The first law of thermodynamics is a special case of, yes. It's a Boyle's law, no. Charles law, no. Yes, it's a law of conservation of energy. This would be the correct option. Let's look at the second question. That question says, when the amount of gas dq is supplied to the system, it performs a work dW.
The increase in its internal energy du is, that means we have this relation, it's a delta q is equals to delta u plus delta w, and when the situation is something like this, then it's a delta u that should be equals to delta q minus of delta w. So this would be the correct option. Next, if the heat energy dq is added to the system, it is taken as, yes, it is taken as a positive. And if heat energy dq is removed from the system, then it is taken as negative. I hope this is clear. Great. Next question, let's have a look. The question says an electric heater supplies a heat to a system at a rate of 100 watt. Great. That means the delta q is given, that is of 100 watt. It, if system performs the work at a rate of 75 joule per second, that means the delta w is given, it's a 75 joule per second, or it's a watt. At what rate its internal energy increases? So we have the relation which is delta q is equals to delta u plus delta w, and from this it's a delta u that is equals to delta q minus delta w, which is equals to 100 minus 75. It is the 25 watt. I hope this is clear. Is it? Is it clear? Are you sure? Are you? Great. So let's work for the next question. Let's have a look. If system has, or let's, if 200 joule of energy has been added to the system and 30 joule of work is done on the system, find out change in internal energy of system. How will you find it this? How will you find this? They say a 200 joule of energy has been added to the system and 30 joule of work is done on the system. We need to find out the change in internal energy. That means when they said it's a 200 joule of energy has been added to the system, it is the delta q which is equals to plus 200 joule, and 30 joule of work is done on the system. That means delta w is equals to minus of 30, it's a minus of 30 joule. What I need to find out? I need to find out the change in internal energy. So let's do it quickly. It's a delta q which is equals to delta u plus delta w. Delta q, it's a 200. Delta u, that is what we want to require. It's a minus of 30. So this delta u is equals to 200 plus 30. This is 230 joule. I hope this is clear. Is it clear? Is it? Are you sure? Great. So let's wind up this session over here. This was all about the first law of the thermodynamics, which is based on the law of conservation of energy. Please go through this and revise this very carefully, because on the next lectures we are going to discuss different thermodynamic processes, and when we will discuss this thermodynamic processes, that They are having a certain characteristics of their own process, as well as we are going to use the concept of the first law. So please go through this very carefully. Try to make as many questions as possible. Thank you. Have a good day. Take care. Bye bye.